So again, thanks for you guys coming in. Just to let you know, there will be catering and food and drinks after. It will be arriving at 6. So if anyone wants to stay a little longer and also like chat with Phil for any questions about after the presentation, that'll be available. But I'm James. I'm the computer science president. Me and Professor Lickman try to set up this event for guest speaker. Um, I don't have much to say other than that. So to get it started, please welcome Phil.
Yeah, thanks for having me. You guys forgot about the Artemis 2 launch. It's happening right now. 53 years back on the moon, and you're here. Thank you very much for that. We're talking about machines and when machines work, but we don't know why anymore. And that might be a problem, might not be a problem. It surely is quite interesting, and more interesting than when we know why and when machines are working. I think I've seen most of you here. I've been around the block quite some time, worked with a lot of exceptional people at different institutions in Europe and in the United States. I founded Mnemonic AI 2019 with my great co-founder Elliot, who's probably watching right now. And we have a research arm that is called M&A Labs, all based in Austin. And I love math, I love AI. And I will talk to you about when AI works, but we don't know why, because AI is what we mean when we're talking about a machine nowadays. But what is artificial intelligence? Can we define it? We can sure as hell look it up, but I think Merriam-Webster does not have a very good definition of it, explanation of it, but it's the most common used capability of computer systems or algorithms to imitate intelligent human behavior. Not sure if that is, I think the clicker stopped working. Yeah, can you push button to move on to the presentation because the clicker is not working? Thank you. You guess what AI really means and what this definition says is as good as mine. What we mean when we talk about AI most of the time nowadays is ChatGPT, right? That is what everyone says is AI. That's, to my opinion, not really the full truth, and I think I can prove it. So artificial intelligence as a term is old, like really, really old. The first mention about artificial intelligence is from 1920. So a long, long time ago. More current is machine learning and deep learning as topics. And the definition, the first one of artificial intelligence was keyed in the 1950s at the Dartmouth Conference for Artificial Intelligence. Techniques allowing computers to copy human behavior. So we're not really talking about having capabilities on their own or intelligence on their own. The most prominent one is the Turing test, where a proband C gets two texts, one from a computer, one from another human, and he or she has to decide which text is which was written by a human. And that was defined as a test if it's true artificial intelligence. Most of the times, most of artificial intelligence research is actually done in marketing departments. And it has a history of over-promising and under-delivering actual value. So we're talking about AI summers and AI winters. Especially the one in the 70s was really devastating. Prior to that, lots of companies said, hey, we can help in the Cold War. We can decipher what Russia is doing. We can decipher the Russian language automatically. It turned out they could not. And so DARPA and the military cut all funding after something that was called the Light Hill Report. After that, it slowly picked up again with expert systems that are not close to artificial intelligence. And if you're a little bit older, you might remember Deep Blue, that once won Jeopardy. And chess games, and then deep learning really took off. And we're still somewhere in the AI summer in the third one. Machine learning is a more technical term that we need to understand when we want to talk about AI and how we can understand AI. It's a technique allowing computers to learn to solve a specific task, not like general intelligence, but a specific task. You know that example, to predict the price of a house based on number of rooms, school district, square feet, and all that. That is the most common example, I think, of machine learning in general. And we can plot it with a linear line. We can take a non-linear model, then it's not linear regression anymore. And the system gives us a prediction based on number of rooms, location, what a house should cost or will cost. That is pretty easy. We give the system data, we give it an objective, and it figures it out somehow. Deep learning goes a little bit deeper. It is machine learning, but it does not use simple algorithms. It uses multi-layer neural networks to come to a conclusion. And thus can learn much more complex representations of data. We have an input layer, we have hidden layers, and we have an output layer. The real magic is happening in the hidden layers, where we can apply different weights to the input data that we have. A weight can be that this information is not important to answer our question, or it's super important, so we elevate or degrade the data. We can do it in lots of different funny ways with math. Sigmoid function, I showed you that it's the output 1 or 0. So do we pass a signal or do we not pass a signal? That is most of the time the question we want to answer. And all the architectures of neural networks, so we can combine these single neurons to really funny ways to get different outcomes, thus enabling us to do crazy stuff with it. We can give it a picture, and the neural network can decompose this picture and learn what content on a picture helps it to identify if it's a dog or not. That can be the outline, it can be textures, it can be broad shapes. That is a pretty common problem that we have when we need image recognition or image analysis. That is what it looks like when you look inside what a neural network is doing. That is a convolutional neural network, and a picture of a cat and the different decompositions. So the system learns its own representation. We do not tell the system, hey, count the number of legs to determine if it's a dog, or look for white spots, black spots. Does it have floppy ears? It learns it itself. And we don't define the features there. So now you've seen how these systems can learn, but the more important question is actually, what are we training them to learn and to do afterwards? And then we know perhaps how they work or not work. So when we talk about AIs, we're talking about two AIs. We have discriminative and generative AI. Discriminative AI is pretty simple. It helps us classify data. Is it a dog or is it a cat? Or is it a horse or a dog? Generative AI creates more. If I give a generative AI system lots of pictures of dogs, it can create a new picture of a dog for me. And that is an example. We use lots of images from more or less famous paintings, and the system then tells us, hey, this might be a Van Gogh or not. And it gives us a probability of being so. Another simple example that shows a problem with machine learning is it a wolf or a husky? That should be pretty easy, right? We can do it. A kid could do it. When we teach when we teach a system, we get this results. Most of the time it's true, but there are some wrong ones, right? And down here, it predicted it's a husky, but it was a wolf. Over there, it predicted a wolf, not a husky. But why did it do that? So we can decompose it, and that is one picture of a husky, where the AI told us, hey, this is a wolf. And then we look at the explanation, and we see the AI didn't even look at the animal. The only thing it picked up on was, is there snow on the picture or not? Because in the training set, all wolves happen to be photographed in the snow. So AI learns what is easiest to learn, not necessarily what is correct to learn. That is important when we talk about, do we understand how it works? And on a side note, this can be used pretty easily to attack AI systems that wants to classify something. You see a picture of an ice bear. Model says with 85.8% confidence, this is an ice bear. Makes sense. We add just some noise into the system, and now it's 100% confident that it's a dishwasher. That can be used to manipulate systems where AI is used to make decisions. So, in comparison, generative model, training data, observations, horses, create a picture of a horse that it is not in the training data set. What about LLMs, right? That's why you're here, you want to hear about ChatGPT. So LLMs are pretty much image generators, but for text. That is the simplest explanation I came up with, and it's the wrong one. In 2017, this paper was published, attention is all you need. Someone said, hey, perhaps it's not just the words we need to compute with, but perhaps the order of the words is important. So we need to teach the AI where to pay especially attention on it. And he called it, or they called it, BERT. That is called bidirectional encoder representations from transformers. That is an easy thing to say. What it means is this. We apply a matrix to each token, to each word in a sentence, and we encode the position of it. And then the system learns, hey, if this specific word is in this position, it might be more important than at the end. Like a word in the beginning of the sentence might be more important as the same word at the end of the sentence or in the middle. And we do that at scale, and then the LLM gets really, really good at predicting what is next. And that is all the magic behind LLMs and ChatGPT. But even smarter people thought, hey, we have so much data, like the whole internet, and all the books, and all the movies, and all the comics, and whatever it is. What happens if we feed that into an LLM? When we had the problem, hey, the LLM might not be big enough. Back then, no one talked about large language models. But perhaps we should make them large, and even larger. And we stack these over another and pass the data through all of them, like millions and billions of parameters. And lots of companies did that. This reaches until 2023. We're right now in 2026. We left the billions of parameters and we're in the trillions of parameters. And then something happened. Magic. And we don't know why. By feeding all this text and videos and images and sound we have into some kind of large language model, but especially text, suddenly the AI learns new stuff it isn't trained for. It should predict the next token, but suddenly it has an understanding of grammar. That makes sense, right? It reads a lot of text, and it memorizes facts, and it starts reasoning, and sometimes even coding now, right? Coding agents, cloud code, codecs, whatever you call them, they start doing the job of programmers. And that is called emergence. And we have no idea why that is happening. There are some theories. They say, okay, finally the models are big enough to understand all the data we have. If it's true, we don't know. And much more interesting is that it's not a linear ascent. So you would expect we make the model bigger and the capabilities, the skills of the model rise in the same way. That's not true. It's like a stepwise increase. We reach some inflection points, or breakthrough point it's called here, and suddenly the large language model has a complete new set of skills, if you want to think of it that way. But what happens inside it? What happens to give LLMs these capabilities? We can look inside them. There's a great tool from Dr. Charles Martin, Weight Watcher, that allows us to measure what is happening inside of large language models. It's not 100% correct, but if we look at eigenvalues, we can determine how much signal is going through a part of a neural network. And if we look at the alpha scaling, how strong is it? How important is it? And when we do that, we can list it down for every part of a large language model or for a neural network. And then we see a lot of these billions and trillions of parameters are not doing really anything, much. So, and what would be the reasonable thing to do? We said, okay, we don't need them. We prune them. You do that in your garden. You cut things out, and we cut out full layers or just neurons from our neural network because we don't need them. They're not contributing anything. And that is as if you would take an orchestra and remove all the silent instruments. What happens? Your output, the symphony, or the output of an LLM deteriorates. So it's not as good anymore. And suddenly it starts losing capabilities of doing so. And that is what is called LLM degradation or decay. So what we can observe is that what looks like noise, like slow signal, low signal, seems to have a structural function inside of AI. And these emergent abilities, these new abilities, suddenly starting to code or make reasoning, seems to rely on these weak interactions that are almost under the threshold to measure for us. And we can take all these measurements we have of what is happening inside an AI and rank it. But we cannot map meaning or behavior back to the components of the LLM we are using. We cannot do that. We don't know what's happening. Even if we do it, we rip the model apart, put every part of the model somewhere different and monitor it and measure it. We cannot explain to you why now LLMs have distinct features. We don't know. Is that bad? Don't know. Let's look at nature. That is our brain, or that image of our brain rendering. So, our brain. You might know we have two hemispheres, right and left brain, and these are connected by the corpus callosum. That is the part in the middle of the brain that interconnects both hemispheres. So sometimes you want to sever these connections, especially when heavy epilepsy or something like that. We cut this. That is 100% survivable. But something strange happens because we have something that is called a chiasma, so a crossing of neurons inside our brain. So everything we see with our left eye is actually processed on the right side, and vice versa. And when you move your left arm, you're using your right brain. Make sense so far? Because now the fun starts with an experiment Sperry and Gazzaniga did in the 60s. They built an experiment where they could divide what they show each eye, and with that, every brain half. And we had the problem, so you showed on the left side a hammer. That was processed in the right side of the brain. But the right side of the brain did not have any connections back to our verbal cortex, so it couldn't talk about what it saw. Make sense so far? So the right hemisphere couldn't process the signal in a way to give it to the left hemisphere, and so the left hemisphere couldn't say, hey, I saw a hammer. It said, I saw nothing, because it operated the right eye. And they then did an amazing experiment. They showed the same province, a chicken leg, and snow for each eye. And then they asked them to pick a card that represents most what they have seen. So, the proband picked a snow shovel. And then they asked, why? But he actually did not see the snow in his left hemisphere. So there was nothing the left hemisphere could talk about. The left hemisphere saw the chicken leg. So they asked them, why did you pick the shovel? And they started talking about very fluently, yeah, you know, if you have chickens, they are in a hen house and you need to clean it out, and doing it manually is really complex, so it's tiring, so we just take a shovel to make it out, to clean it out. And that is called left brain interpreter. So our left brain interprets our environment. And even without full information, like it was missing the visual input, it can come up with a story about it when it's asked to. And that is pretty much what LLMs do. Even if they don't know something, they start giving you at least solid sounding answer about what you asked it. But the LLM, as well as our severed brain, cannot distinguish between truth or false. It just goes by plausibility. That is not a bug. That is what intelligent systems seem to do, because we're, I think, one of the more intelligent systems on this planet, and we behave that way. So why should LLMs behave differently in the first place? So perhaps when we think about, can we understand AI, and can we see what AI is doing, perhaps the problem is us and not the AI. Perhaps we think wrongly about AI. If you look it up in the more classical literature, you often find intelligence is defined as logic, as rules, as reasoning. But as these experiments with humans and with LLMs show, perhaps intelligence should better be defined as a way of pattern extraction and predicting on that pattern. But in the end, these AI systems they do not think, and especially not like us. And that's what makes them powerful. Because it's not just a replication, perhaps doing it faster, stronger, cheaper than we think. It's a novel way of solving problems. And that comes with a big trade-off. And that is, I think, at the heart of the discussion about AI right now. We want AI that can do more things, do things better, so increase the capability. But at the same time, with it, the interpretability. So why is AI doing stuff goes down? And that is nothing new for us as humans. We've seen that before. Our brain, again, is a good example. If our brain is so simple that we can understand it fully, our brain is too simple to use it to understand our brain. That is called catch-22. With dinosaurs, in the 1800s, we knew that dinosaurs were dragons. Without a deeper understanding about genetics and evolution, we knew in the 1900s, and at least 50 years ago, we knew that they were reptiles. Now, currently, we know that they are birds and probably had feathers and didn't look anything like that. That is how we know different things. They still work. Evolution works, no matter if we understand how it works. And I think the most prominent example is electricity. We used electricity long before we understood how it worked. Think about the poor elephant Tupsy in New York when they electrocuted it to show if electricity is dangerous or not. We didn't have a full understanding of electricity, but we already used it. So I think we need to change how we think about AI systems. We cannot rely on our intuition anymore because it does not follow our intuition. But we must validate empirically if AI is doing the right thing or not. And if we think of it as an intelligence that is different from ours, an artificial intelligence that is different from ours, we definitely need some guardrails. What we want AI to do and what not. We need to discuss it as a society, actually, what we want. But, so, finally, what is AI and how does it work? Because that was the question that brought us here. AI is a system that does not understand the world like we do. It has its own understanding, and probably every neural network has a distinct, different understanding of the world, because its models are different. It learns to model some kind of structure of the world that might be a completely different structure that we use. Think back at the example of the husky and the wolf. We would look at the actual animal to distinguish it. The AI said, hey, the structure using snow or not snow just makes much more sense from the small segment of data it had that described the world to it. We don't understand AI, and I think that is long gone. We will never come back to a point where we fully understand how AI works. And talking mostly to students here, I think your big advantage will be when you can make the leap of faith, if you want to start working with systems that work beyond your intuition, that behave different than you would expect them to behave. And I think that will become a daily life, especially for you. You are much younger than I. The system will get more complex. And with more complexity, the capabilities will rise. But the intuition will go low. We will even less understand how it all works. Probably in 5 years, we cannot look into it anymore and have just the faintest idea what's